we talk a little here about some details with friction. All right, friction. There's some pretty neat phenomena that happen, and some main points to touch on. Here's one of them. There are some things that we call properties of matter, like inertia. Objects have inertia, right? Objects have mass. Objects, occupy volume. Objects don't have friction, right? Friction only exists with a two-object combination, all right? At least a two-object combination, and it comes from contact between objects or surfaces. That's a big deal. For example, a box and a table. A box slides across the table. There's friction there. Now, the amount of friction between the box and the table, the steel box and the wooden table, might be different from the amount of friction between what? Well, maybe a wooden box on a wooden table. Oh. All right, so there's something with friction that has to do with material, or really what the surfaces are made of. Okay, we'll get to that more specifically in a minute, of course, after I have to do this, which is the most annoying thing ever. Especially with this here. Okay, now, further, if we look at every combination of steel box and every wooden table, and again, let's assume that wood is just wood. There's not even any variation in wood. But if you look at every box, every steel box and every wooden table, there's not even the same amount of friction. All right? And so, if we look at how much force is required to, say, push this box at a constant speed, right? Well, we'd have to push with an applied force A that's equal to this friction force. All right? So, let's say this box weighs that much. There's that much normal force. Okay? Now, well, what if we had a box like this? And what I'm trying to represent here is that a much bigger box is by necessity much more massive. Well, we might have here a box that weighs a lot more, and therefore it takes a lot more force to push because there's a lot more friction. Make sense? It's certainly harder to slide big, heavy things around than it is to slide light things around. We all agree with that? So that says that friction seems to be related, like we said over here, that there's a certain relationship between friction and the kind of stuff that things are made of. Right here it says that friction looks like it's related to, well, in this case, on the right, we require a bigger applied force A because there's more friction, and that seems like it could be true because this thing weighs more. So it could be that friction is related to weight, or maybe even to mass. Or the one big thing also is not only does weight change as this object, well, weighs more, it also changes normal force. So it might be that friction is related to normal force. Right? Well, which one? Let's continue and see. So we'll imagine a case like this. You got a box and you're sliding the box up the wall. That old routine. So, this box, let's say here it is. Oops, sorry, wrong way. So the box weighs something, right? And if we want to slide it up the wall, well, let's say we push with a force A like that, okay? Well, by us pushing, there's a component of our applied force that points in towards the wall. It means that there's a normal force that points out like that, right? And, if, let's say, with this applied force, it's quote-unquote easy to slide it up the wall. What if I wanted to make it harder to slide up the wall? Oh, now what I should put also, of course, is if I'm going to push this thing up the wall, well, there's a friction force down it, right? Make sense? Sure. Now, same block over here, weighs the same amount. The question is, what would I have to do in order to make it, quote unquote, harder to slide up the wall? Or really what I'm saying is, in order to make there more friction, make there be more friction between the block and the wall. Well, what ends up happening is if I push harder like this into the wall with a bigger applied force, well, that's going to make more friction downward. Can you imagine doing that? I mean, literally, put your hand against the wall, run it up and down the wall, and then push your hand into the wall and run it up and down the wall, and it's a lot harder to do. And the reason is because now there's much more normal force. All right? So what we see over here is little normal force, little friction force. Here we see bigger normal force, bigger friction force. Our conclusion, I hope, is that frictional force depends on normal force. Fair enough? Okay. How are they related? Well, they're related, really, directly. Frictional force is proportional to normal force. And really, you can always replace a is proportional to with equals a constant times. All right, so we say that friction force equals mu. It's not really spelled this way, but it's said that way. Mu, it's a Greek letter mu, which looks like if you were to write it, hang on one sec. So, as I was saying, I think that mu is like a U with a tail on the front of it. All right? Okay. So, what is this thing, mu? It's called the coefficient of friction. All right? It's literally what it's called. And, well, one big deal about it, right? If we solve for mu, we get F divided by Fn, and that would be newtons divided by newtons. Therefore, mu does not have any units. It's called a dimensionless quantity. All right. Yeah, it's not a force. Right. It's literally a constant that exists for any combination of two surfaces or materials, and it depends on what the stuff's made of. It depends on literally like kind of microscopic, subatomic, really, or atomic level properties. Okay. Yeah, so for example, here's a couple. There's this big old text reference called the Handbook of Chemistry and Physics. I looked up some of this stuff. So there's a coefficient of friction for unwaxed hickory and dry snow. So imagine a big old book written a long time ago, this reference. So this unwaxed hickory and dry snow is like skis, or like runners for a sled that used to be made of wood, right, on snow. Dry snow, I don't know, as opposed to, that's like powdery snow. So this 0.08 is kind of as opposed to this one down here, vulcanized rubber and concrete. Well, vulcanization is a process they use to make rubber, I don't know. But tires are made of vulcanized rubber, and roads can be made of concrete, right? So this is typical tires on the road sort of thing. So what you can see is with a small coefficient of friction here, right, that's going to make forces of friction typically pretty small. And with big coefficients of friction here, relatively, this is going to make a pretty high amount of friction. All right, big deal. Mu is always less than 1. Always not really true. Anything that you ever solve, though, that will be the case. If you get more than 1, you've done it wrong. I guarantee it. All right, I'm going to make my mu's nicer to get you in a better habit of how to draw a good mu. That's better. Okay, always less than 1. You'll always get less than 1. Okay, a couple of cases here. Oh yeah, I want you to try to do this one at home. All right, what I want you to imagine is that you're drawing a graph of the force required versus time to do what we say here. To get a block, you want to set it into motion. Really to push like real gradually. You push a little bit, it doesn't move. You push a little harder, it doesn't move. You push a little harder, it doesn't move. And you push until it just starts slipping, and then you push hard enough to keep it moving at a constant velocity. I want you to try to draw this graph, all right? And there are kind of these two phases. First, I'll say you push. Gradually harder and harder until a block slides. And then phase two, you push hard enough to maintain constant velocity. All right, see what you can come up with for that. Don't look it up, just do it. Try. Okay, now, yeah, there's really two kinds of friction. How you doing, Martha? Martha's here. Say hi, Martha.
Hi.
Good, very good. Now, two kinds of friction. One's called static friction, okay? We've heard of this thing called static friction. Or we've heard of static at least, right? And static is, means not moving. So static friction is a force of friction that can keep things from moving, or that exists or acts right until something slides. All right, you'll see that in some problems. You'll hear that. You'll see those words. It'll say something about object just starts to slip, or object is just set into motion, or right up until something slides. You'll see those words in problems. All right, and because there's this kind of friction we call static friction, there's this coefficient of friction that we call the coefficient of static friction. All right. And then there's kinetic friction, which acts as objects are actually sliding across each other. Therefore, a slightly separate equation here that has what we call the coefficient of kinetic friction. All right. Now I'm putting FNs here. If you just want to keep writing N, that's okay too. All right. Now notice a couple of big things. Here's a big thing. All right. The bottom line is, if there's a block just sitting there like this, well, certainly it weighs something. Certainly there's a normal force. But right now, if it's not being pushed, there's no friction at all. None, right? Friction opposes motion. And in this case, there's nowhere that thing wants to go. If we put this block on a little bit of an incline, right, now we get a weight force like this. We get a normal force like this. We get a little bit of friction, right? If we put it on a steeper incline, we get weight, same. We get normal now like that. We get a little more friction, all right? So that says that static friction can range, I'll say this, it can range from 0, there doesn't have to be any, up to some maximum value. And the maximum value it can be is mu static times the normal force. It doesn't have to be that much. That's the most it can be. All right, but for kinetic friction, there is always exactly that much. If something's moving, that's how much kinetic friction there is. All right? Yeah, so I think the last thing we said was no matter how fast or how slow something's moving, when there is kinetic friction, there is that much mu k times the normal force. Here's a big question. Which one's bigger? You'll see kind of on the next page. But we got to talk about why that is. Remind me of that. Remind me to talk about why this is. Great little discussion. And it ties in with our graph also, that graph I asked you to look at. Okay, so a couple of situations here. Let's see. We got a block sitting there on concrete. Here's some information that I give you. There's the static coefficient. There's the kinetic coefficient. There's the mass of the block. We'll use 10 for G. Okay? So first of all, let's find normal force, right? Well, here's the weight force. There's the normal force. Nothing here about angles, so we can just say that normal equals weight, which is equal to mg. Fair enough? So that says that's going to be 100 newtons, right? 10 times 10. Okay? Okay. Now, over here, you know, how hard can we push before this thing starts to slip? Well, you know, this is primo keywords for static friction. And really, for maximum static friction, all right, just before it starts to slip, we could push a little bit, nothing would happen. We could push a little harder, nothing would happen. A little harder, nothing would happen. Well, how hard can we go until this thing actually does something? We'd have to get to the maximum amount of static friction, all right? So we were really looking for this, FFS max, so many subscripts, equals in this case, mu f times the normal force. Hang on, Shanks is here. Hello. When you stop. Go ahead. Talk. I don't know what to say.
An applied force of 40 newtons to the stationary block.
That was Shanks.
No, it wasn't.
Shanks, that's Shanks. It's a real handful. Yeah, okay, so, yeah, okay, well, we have our normal force, we have our static coefficient, so this says that, oh yeah, now, what I should say is, if we want to get this thing moving, we have to apply FFS max, enough force. Well, we have to apply a force that's equal to this static friction force, or really just a touch more, but it's, you know, it's so much less that it's so little more. Like, it doesn't make any sense. You know what I'm saying? Right? This is really FFS max comes out to be 50 newtons. So we have to apply, you know, infinitesimally small amount over 50 to get this thing to move. All right, but saying 50 is fine. Yikes. All right, now, the question here is, well, what if we apply a force of 40 newtons to that stationary block? Well, first, what's the force of friction? Well, what we have here is the maximum amount of total possible static frictional force. But the static frictional force can range from 0 to 50. All right? The most it can be is 50. If we apply only 40, well, there's going to be only 40 newtons of static frictional force. And what happens? Nothing. Nothing at all. Right? We have to apply 50 newtons to get the block to move. We only apply 40, well, we get 40 newtons of force, of frictional force to resist that 40 Newton applied force, but it's not enough to set the block in motion, so nothing happens. I'll say not enough FA to overcome FFS max. Okay? All right, next. Things look a lot similar here, except now we're talking about the thing moving. Okay? How much required to move it at a constant velocity? Well, as soon as you see something about motion, we are talking about FFK. Right? Here's the weight. Here's the normal. Again, it's 100 newtons like it was in the last page. If we want to move this thing at a constant velocity, we apply a force equal and opposite to FFK, right? I'm sort of getting away here from writing net force in the x equals 0 and A minus FFK equals 0 and therefore A equals FFK. I'm sort of skipping to that step. On a test, you'll write all those things, of course. So there's how much force we have to apply. Well, that means that it's mu kinetic times the normal force that's equal to A. And that means it's, in this case, here's mu K. We apply 25 newtons. Remember in the last page, it took 50 newtons to get it moving. Once we get it moving, it takes only 25 newtons of force to achieve constant velocity, or to keep it moving at constant velocity. Right? Now, dig this. What if we apply 40 newtons of force to that moving block? Well, A, what's the force of kinetic friction? It's the same exact force it was before. FFK is always mu K times the normal. It is always 25 newtons. Okay? If we go ahead and apply a force greater than that frictional force, I'll do this also. Well, what happens? We get A minus FFK equals m times acceleration, and this block accelerates, right? Acceleration is A minus the frictional force divided by the mass. So that's 40 minus 25, 15 newtons over the mass, 10 kilograms. We get a 1.5 meter per second squared acceleration. All right, just so we're sure, on the last page, oh boy, oh boy. What? Stop, stop. Why must you scroll all the way through? That's, all right, I can't do anything about that. On the last page, we applied a 40 Newton force to the stationary block, and nothing at all happened. That wasn't enough to overcome that maximum static frictional force. Here, we apply 40 newtons of force to the moving block. It's more than the total possible kinetic frictional force, so the thing has to accelerate. Shanks, interrupting me again. All right, so I'm going to leave it there for now, for today. All right, so that's a kind of a quick one. Kind of a lot to swallow, though, so I didn't want to go ahead and do a whole example. All right, so tomorrow, quiz, static equilibrium. What's up? I'm talking about 2 problems. All right, one's going to be super straightforward. One's going to be a little harder. Probably not as hard as question 5 in that homework. I don't need you to be able to do the sine divided by cosine is tangent thing, okay? But yeah, it'll be harder than your plain old symmetrical. Here are the 2 tensions. Find me the weight. The second one will, at least. Okay. Okay, folks. See you later.